Hello, my name is Qinggang Wang, a PhD candidate from Huazhong University of Science and Technology. It's my honor to be here to share our recent work entitled GraSU, a fast graph update library for FPGA-based dynamic graph processing. Graph processing is ubiquitous in our labs, like information tracking, recommendation systems, and so on. In recent years, hardware acceleration has been demonstrated to efficiently boost the performance of graph processing. In particular, FPGA can be regarded as one of most promising hardware platforms for graph processing due its fine-grained parallelism, low power consumption, and flexible configurability, showing impressive results. Unfortunately, most of existing FPGA-based graph accelerators are designed for handling static graphs. In fact, real-world graphs are often subject to change over time, aka dynamic graphs. For instance, the Twitter graph may be updated with 6,000 tweets per second. To process a dynamic graph, it often relies on an iterative process with two basic kernels, graph update and graph computation. Graph update aims to generate a new graph by modifying a graph snapshot with addition and deletion operations up on a vertex or an edge. Graph computation, which can be a graph algorithm or an ad hoc query, is then performed based on this new graph to extract useful information. Previous studies show that graph update can function as importantly as graph communication. An inefficient graph update may lead to an expected outcome. An example is financial fraud detection, which aims to find fake transactions using the ring detection on dynamic graphs. In this case, a slow update may cause the ring detection to operate upon an outdated graph such that the results can be inaccurate or even useless. Although early studies on traditional architecture use novel graph representation to improve the concurrency of dynamic graph updates, their underlying efficiency is still limited due to the inflexibility of traditional memory subsystems. In this context, graph computation has been well studied in existing FPGA-based graph processing accelerators, while graph update is still understudied significantly. In this work, we expect to develop a specialized FPGA-based graph update library that can be easily integrated into any existing static graph accelerator so as to support dynamic graph processing with minimal hardware engineering efforts. However, performing graph updates efficiently on FPGAs remains challenging. For a typical FPGA-based graph accelerator architecture, vertices are often stored in the on-chip VRAMs to reduce random access overheads of vertex state, while edges, massive in quantity, have to be loaded in a streaming apply in a streaming apply function from the off-chip memory. In this context, a graph update operation can be split into three basic steps. Consider an edge update. First, the source vertex index of the to-be-updated edge is read. Its edge array will be loaded from the off-chip memory and stored into the registers attached to each processing element. Second, the to-be-updated edge is then inserted into or deleted from the loaded edge array, which is finally written back to the off-chip memory. In the real world, there often are a large number of updates applied. The off-chip edge data may be rapidly and redundantly accessed by each PE, therefore resulting in expensive off-chip communication overheads. To demonstrate this, we conduct a set of experiments to break down the real computation time and off-chip communication time of graph updates operating over AccuGraph. We see that communication overheads dominate the overall execution time of graph update. Therefore, we focus on addressing whether and how the off-chip communication arising in dynamic graph updates can be transformed into on-chip memory access. We observed that dynamic graph updates operating upon real-world graphs showing significant spatial similarity for off-chip edge data access in the sense that most random off-chip memory requests come from accessing the edge associated with a few value vertex. Consider the real-world dynamic graph wiki. About 99% of edge updates are associated with only 5% of vertex. Spatial similarity motivates us to classify the entire edge data into high-value data if it is requested by many edge updates and low-value data otherwise. There is a significant gap between FPGA on-chip memory and off-chip memory that cause problems in some applications. Fortunately, there's a new memory in the system design hierarchy, and it's called UltraRAM, which can provide much larger on-chip memory resource to fill that gap. Therefore, both of them motivates us to reduce the most off-chip communication overheads by applying a differential data management in which for each batch of graph update, high-value vertex edges are resident on the specialized on-chip UltraRAM, while most of low-value ones are stored in the off-chip memory. Besides on this insight, we propose GraSU, a fast graph update library for FPGA-based dynamic graph processing. Our first contribution is a value measurement which enables accurate estimation of the value of a vertex. Another value-aware memory management which returns high-value data on-chip so that most off-chip data communications arising in graph updates can be transformed into fast on-chip memory access. The first thing is to locate this frequently accessed data. A direct approach is to predict using the vertex degree. However, as shown in the right figure, the accuracy gap between the degree-based approach and the ideal case become bigger as the update batch is processed to make a precise prediction. We quantify the value of a vertex depends on not only its degree but also historical update frequency. Where this new approach is accurate, its overhead can be large. Fortunately, we found that the interleaving between graph update and graph communication offers a chance to hit the overheads. Based on the quantified vertex value, the next step is naturally to identify the high-value data that should be stored on chip. GraSU tries to store as much high-value data as possible on chip, since the value and the age number of each vertex are changed over time and the on-chip memory size for different FPGA is different, we must dynamically compute the high-value data. In this differential memory architecture, both UltraRAM and the off-chip memory have the age data. Thus, we must know which memory and where the corresponding age data are located when a vertex is processing. A naive approach is to use another offset array to record the on-chip age data, but it incurs extra space overhead. We present a simple yet effective bitmap-based method to yet a good trade-off between space overhead and memory addressing efficiency. More details can be found in this paper. With the above designs, GraSU can efficiently handle dynamic graph updates, and other important things is to integrate the GraSU into an existing static graph accelerators with minimal hardware engineer efforts. As shown in the figure, we provide a uniform programming framework. Users only need to instantiate the accelerator module inside the top module, and then connect accelerators input-output signals with other GraSU modules. To evaluate our work, we integrate GraSU into AccuGraph to perform dynamic graph processing, referred as AccuGraph D, running at Xilinx U250. We choose Aspen and Qinggang as baselines and run them at a high-end server. 3 graph algorithms are selected to tested on 5 real-world dynamic graphs. AccuGraph D outperforms Qinggang and Aspen by an average of 30 times speedups and 4 times speedups in terms of update throughput. In addition, we improve further overall efficiency by 9 times speedups and 3 times speedups on average. We finally explored to integrate GraSU into other 3 FPGA-based graph accelerators, including FabGraph, WaveScheduler, and ForGraph. Results show that the dynamic graph versions of FabGraph, WaveScheduler, and ForGraph integrated from GraSU also outperform Aspen, showing the generality and practical ability of GraSU. In summer, we introduced a graph structured update library. called GraSU for high throughput updates on FPGA. GraSU can be easily integrated with any existing FPGA-based stack graph accelerators with only a few lines of code modifications for handling dynamic graphs. GraSU features with the two key designs an incremental value measurement and a value-aware differential memory management. The first enables to quantify the date value accurately, while its overheads can be fully handled behind the graph computations. The latter explores spatial similarity of graph updates by returning high-value data on chip so that the most off-chip data communications arising in graph updates can be transformed into fast on-chip memory access. Our evaluations shows that AccuGraph D can run much faster than Stinger and Aspen. Thanks very much for your listening.